What we are going to look at for the next hour and 15 minutes or so is one of my favorite topics, in-memory OLTP. I'm going to give you a somewhat fast overview of the basic principles for those of you that have maybe just heard about it, but not really looked at any of the inner workings of it, really don't have any concept for how it does what it does. So there'll be an intro looking at the basics, but then I want to tell you some of the things that have been added since the initial introduction of in-memory OLTP, which was added to the product initially in SQL Server 2014. Is anybody using in-memory OLTP in production? Awesome, thank you. I'm going to, as I tell you some of the basics, I'll also tell you some of the ways that you can easily get started with this technology. If you're not ready to turn your whole database over to in-memory tables, there are ways you can take really powerful advantage of the technology just a little bit at a time. I'll mention some of that as we go through the basics here. My name's Kalen Delaney. I've been working with SQL Server for a very long time, but just 6 weeks ago, I finally, or actually, or add some other adverb there, started working for Microsoft. All these years with SQL Server, and I was never a Microsoft employee. I started my SQL Server career as a Sybase employee. Then I was independent for several decades. And then just a few weeks ago, I did start working for Microsoft. It felt like, you know, a circle of life kind of thing. So here I am, and this may be where I end my career. Thank you. Still doing a lot of what I used to do, writing courses, delivering training, working with the engineers, trying to understand the new features just as deeply and completely as I can. But now I'm doing it for Microsoft with a regular paycheck, which is a really nice thing, let me tell you. All right, so we have the usual warnings and caveats here from past, the normal commercial here telling you all the wonderful things that you can explore and experience here at the past summit in beautiful Seattle. Seattle is my local area, not the city itself. I used to live about 2 hours west of Seattle. Ooh, think about your geography. Where is west from Seattle? And then just recently, like the week after I started working for Microsoft, we moved to about 2 hours north of Seattle. I did that because I got a new granddaughter about an hour north of Seattle. So now I'm only an hour north of the granddaughter. I can get to her a lot easier than I could when I was living 2 hours to the west. So, but Seattle is still my airport. Seattle is still my big city. So it's always exciting to be here. And thanks all of you for coming. So again, I said very long time, 32 years as of just a couple of weeks ago. I know the date I started, and as I was unpacking in the new house, I found the certificate that Sybase gave me that says, I survived a year at Sybase with the date, so I know exactly when I started working there. It was October 27th, 1987. So this is 32 years now with this product. I mainly write books, and I have a book about in-memory OLTP, and I found a bunch of copies of the book while I was unpacking, and I thought, I really don't want to keep all these. I'll bring them to the summit next week. I did give away one of them at lunchtime, but I still have 2 left, and I'll try to think about some way to give them out to 2 of you here. So, as I mentioned, I'll give you a basic background of what in-memory OLTP, codenamed Hackathon, is all about. We'll look at the changes in 2016 and 17, but those will basically be bullet lists. This changed, this changed, this changed. But then there's 2 new 2019 features that we'll go into detail on and actually have some demos. There is a revision of the underlying technology, so TempDB now automatically, without you having to do any special setup, TempDB takes advantage of this in-memory technology to store some of the system tables using the in-memory feature, and I will explain to you why that's a really good thing. And there's also a feature called snapshot databases that in my informal polling earlier this week, I found that not a whole lot of people are even familiar with. But I will tell you a little bit about database snapshots, and now in SQL 2019, they are supported for databases that have in-memory tables. So we'll start with just what is this in-memory OLTP all about? And I will also point out, a lot of times when people are talking about a technology, they'll want to shorten it. Saying a whole bunch of syllables takes too long, and we're all in a hurry, we got too much to do. So in-memory OLTP, how would you shorten this? I have heard people, Hackathon, of course, is the way to shorten it, but people that don't know the Hackathon code name I've heard people refer to it as just the second part of the name, just OLTP, especially like when I'm giving a bunch of talks at some event and one of them is on in-memory OLTP, they'll say something about, oh, and do you have the slides for your OLTP presentation? It's like, oh, all my slides are about OLTP. This is what I do. It's like, no, that one over. It's like, no, OLTP is not the crucial word here. It's what this technology was optimized for, online transaction processing, but the crucial part is the first part, the in-memory part. So it sounded like some of you were familiar with the code name Hackathon. Hackathon seemed to have become really popular, and even the engineers at Microsoft still just talk about it as Hackathon. Hackathon comes from the Greek word for 100, the original vision. And I was specifically told when I started working with this product and started writing about it to not say goal, not the goal, but the vision. The vision for in-memory OLTP was to be able to increase performance 100-fold, not 100%, which is just double. Sounds like a big number, but it's just double. 100-fold means 100 times faster or 100 times more throughput, 100 times more transactions per second, however you're measuring your performance or your throughput. And they actually have done an incredible job. They could have made it a goal because they're really close, and there are customers now who have hit that 100-fold improvement in the more recent versions. But even in the initial release in 2014, there were customers in the pre-release product that were getting a 20 to 30-fold increase. The initial version, before it was even released, they were improving performance 20 to 30 times. Then, of course, it just kept getting better and better and better with every single release. Not every workload lends itself to in-memory OLTP. We'll talk about when you might get some advantage from it. So Microsoft describes the benefits in these 4 pillars, these 4 boxes that you see up here, that completely new data structures have been developed for the in-memory OLTP, completely new ways of storing your rows in your tables, completely new index structures, all optimized for this new way of working with data. The data is in memory all the time. That doesn't mean it's only in memory. The question I used to get more than any other when the technology was first introduced was, well, what happens if your SQL Server crashes? Well, the data is not only in memory, it's just always in memory. The SQL Server behind the scenes quietly streams your data out to disk for recovery purposes only. The data is never read from disk during query processing as your normal disk-based tables would be. The data is always in memory from the time your SQL Server comes up. It's there, it's available, you can use it without waiting. But as you make changes behind the scenes, SQL Server streams it out to disk So if there's a shutdown, a crash of SQL Server, when you bring it back up, it knows what the changes are. We're not going to be able to go into all the details of how that happens. It's in the book if you want to read about it. So another aspect of the in-memory OLTP technology is that we have an ability now to write what's called natively compiled procedures. And when I talk about this, what it means is that I have to admit that we've been lying to you all along. We've talked about stored procedures being compiled since day one. We've had a stored procedure called SP recompile. We were lying to you. Nothing was actually compiled. Prior to the introduction of in-memory OLTP, your procedures were translated to an internal form, but they weren't actually compiled. True compilation down to machine code did not happen until the introduction of this native compilation with your in-memory OLTP procedures. So that's something that speeds up performance even more. And when I have another session that deals with performance for in-memory OLTP, and I do demonstrate a natively compiled procedure, we won't be able to see that today. The biggest benefit that a lot of people notice immediately, and also the benefit that people can immediately see how we're going to get big performance boosts, is the fact that there is absolutely no locking. No locking for data access. That doesn't mean no waiting. There are a few things that will have to wait for other things to finish, but locks are never applied and never have to be waited for. So if you've got applications, queries, tables that frequently get blocked because someone else has a lock, that just won't happen if you put the table in memory. There's also no latching. We don't have time to talk about exactly why that's an issue and what exactly that means. Rows are all stored in multiple versions. Every time someone makes a change to the data, you get another version of the row, and then anyone accessing the data, just SQL Server is able to figure out which of the multiple versions is relevant to them based upon the time that their transaction or their query started. This technology is fully integrated into SQL Server. It's not an add-on. You don't even have a choice. When you're installing SQL Server, there isn't even a checkbox that says, do you want the in-memory OLTP technology? No. You install SQL Server 2014 or anything after that, and you have the ability to create in-memory tables. It's fully integrated. All of the tools work with the in-memory tables just as easily as they work with any other tables. You don't even have to specially label the tables. Most people do. They'll put some suffix on their table name so they'll remember that it's an in-memory table. But SQL Server doesn't need your help to know that it's an in-memory table. And you can say, select from my regular disk-based table or select from an in-memory table, and SQL Server will give you the data. It doesn't care. It will get it for you. All the tools, Management Studio shows you the in-memory tables just like any others, and your PowerShell, your SMO, there's dynamic management objects to show you your dynamic management, to show you your in-memory tables and special details about them. We'll actually be using one of them in one of the demos. So this technology, although there were people using it in the very first release, getting major performance improvements, there were some very severe limitations, and it just didn't quite catch on as much as Microsoft had hoped in 2014. And some of the biggest limitations that people complained about was there was no referential integrity possible. No foreign keys could be declared, and then you couldn't even build triggers. Triggers were not available for in-memory tables, so you couldn't define your own foreign key relationships using triggers. You couldn't change the table definition after you created it, and what that also meant was any indexes on the table all had to be defined at creation time, and you couldn't add indexes later or remove indexes that it turned out you didn't need unless you completely dropped the table. No changes to any table once it was created. One of the restrictions I found the most frustrating was the fact that if you wanted to build an index on a character column, the character column had to be using a binary collation, which meant case sensitive. And yeah, I know we have to be aware that some people use case sensitivity out there, but if we have a choice, we'd really rather not. So any column, any character column with an index had to be binary collation, and that was a real tough one for a lot of people. Also, one of the kinds of indexes I'll mention in just a minute is called a hash index. And when you define a hash index, those of you that are familiar with indexes with hashing, should also be familiar with the concept of buckets and bucket counts for hash tables. And when you defined a hash index, you also had to supply a bucket count. And for hash indexes within memory tables, if you didn't define it appropriately, performance would suffer. And a big problem with that is the people who wrote the original sample code didn't understand buckets and hashing and bucket counts. And some of the original samples in the Microsoft documentation would just define 1,000 buckets and then insert a few million rows into the table. And people would try this out and say, this performance is abysmal. And they'd say, forget this technology. Well, a lot of that was just because of not understanding how to choose a good bucket count. I'll say a little bit more about buckets as we go through the background of what in-memory is all about. I mentioned in-memory OLTP. When you create an in-memory table, there are completely new data structures that don't look anything like what you had for your regular, what we now call disk-based tables. So we have in-memory, which are the new ones. Disk-based is what we've had all along. Stored on disk, read in from disk. Pages are written back to disk when you change them. So we'll briefly look at database creation, table creation, a little bit about how the rows are stored, and then the two kinds of indexes that are supported for in-memory tables. They're called hash indexes and range indexes. So when you create a database to allow in-memory tables, it needs a special property. Any database that's going to support an in-memory table has to have a file group belonging to the database. You must alter database, add this new file group with a property called contains memory optimized data. Behind the scenes, this file group acts very much like a file stream file group. If you've used file stream, it should look really, really familiar. But you don't have to do the special enabling of file stream. You can create the file group when you create the database, or you can alter the database and add this later. As long as then you add at least one file to this file group, the file will be where the data will be stored on disk for recovery purposes. As long as there's at least one file in the file group, you can then start creating memory optimized tables. A few limitations, and these still have not gone away even in the current versions. The file group, once you've created it, it can't be dropped. If you decide, I don't want this in-memory stuff anymore, you can't just drop the file group. You'll have to create a whole new database and move all your non-in-memory tables over. You don't specify a size for the files because the truth is they're really not files. You say create this file in this file group, but what you're really doing is creating a folder. And the folder has a bunch of files in it, but the folder doesn't have a maximum size. I will show you that when we create our database to store in-memory tables. And then just a reminder that you do have to have character columns, use a binary collation if you're going to index them. If you're not going to index them, they can use a case-insensitive collation, and you should remember that. You can specify the default collation for the database when you create it, so you could specify that this database has a default collation of of one of the binary flavors. Oops, did I? So table creation looks almost like creating any other table. There's a very few restrictions on what can go in the table. You can't have the legacy large object type, which means text, image, or Unicode text. You can't have a CLR or an XML type, but you can use the max types. Those are the current large object types. Those are possible in a table to be stored in memory. And that's that's one of the changes in 2016. Still, all indexes are specified in the create table. There is a limit of 8 indexes in the initial release. Most of this, except for where I say 2016 there, is what was true for the initial release. I will mention over the next few slides a few of these things have changed. I lied. The DML triggers. We didn't have triggers in 2014. We got them in 2016. Darn, I didn't write that. All right, I will edit the slides before they're published. But we also, in the initial release, had a maximum of 8 indexes. And a lot of people thought, oh my gosh, this is not very many. How many indexes can a disk-based table have? And it's okay to say, I have no idea, but it's way too many. That's actually the right answer. Nobody should ever create the maximum number of indexes on any table, no matter what you're doing with it. But for these tables, the restriction isn't really a bad thing, because now we can talk about the second part of the name of the technology, OLTP. In an OLTP environment, it's usually recommended that you keep your number of indexes to a minimum. Most people will say maybe a handful, and if you got a slight mutation, that might be 6 or 7, but 8 indexes on an OLTP table, which means ones that's heavily updated. A heavily updated table should not have lots of indexes on it. 8 should be plenty, even though later versions change that limit. We'll see what the changes are after we look at the basic storage. So rows are stored completely different in an in-memory table. Instead of being grouped together in pages, there are no pages. In-memory tables are not stored on pages. They're always in memory. You add a row to a table. SQL Server just finds a place in memory to stick that row. Here's a new row, here's a new row, here's a row, here's a row. How does SQL Server know what rows then belong to the same table? The way that the tables have cohesion is through the indexes. The indexes are what combine the rows together into the tables. Without indexes, you just have a bunch of free-floating rows, and you wouldn't know what rows went to what tables. Every row has its data, but I'm not even showing you the data here. Oops, that's not what I wanted to do. I haven't used this pointer in a while. Let's see if I can get it to work. It works. Look at that. I just point at my screen, and then it actually works over there. All right, so there's the row header here, which I'm elaborating on, and I know you probably can't see the small font. And the payload is the actual data. So this is my row. This is my data here, but the beginning part of every row has some overhead information shown down here. Every row has a beginning timestamp and an end timestamp to specify the validity, the life cycle of this row. I mentioned that the rows are versioned. Every time an update happens, a new row is added. Every database keeps a timestamp, which is continuously increasing. Every time anybody does anything, the timestamp clicks up. It's not a date time. It's just an internal counter that SQL Server can know what 2 things happened at the same time, or what happened before something else or after something else. So whatever this internal counter is, when your row was created, goes in the begin timestamp value, and when the row is deleted, that whatever the current timestamp for the database is, goes in the end timestamp value. So you can think of these as like the birth date and the death date of the row. And then any transaction that's running between that birth date and death date will see that row. Transactions that started before this row was born, or started after this row died or was deleted, may see another version of the row, or will see no row at all, if there aren't any other versions. We have a question here.
Does this also happen with the in-memory optimized tables that are schema only?
The internal storage for schema-only tables is the same. Tables can be created as either schema and data or schema only. The basic difference between those two is that the schema only tables do not have their data quietly written to disk behind the scenes, but the storage of the two flavors is exactly the same. Interesting question. So the indexes, as I mentioned, are what combine the rows together into a table. Hash indexes are defined in your create table statement as a non-clustered hash. You specify a number of buckets. The recommendation is at least as many buckets as the number of unique values expected. There's no requirement for that, but if you want good performance, that's usually what Microsoft recommends. At least as many buckets as the number of unique values. Hash indexes are really, really good if you're going to look up a specific value. Select from my table where, and it doesn't have to be unique, just a specific value. Select from my table where city equals Tacoma. Select from my table where price equals $9.99. Select from my table where some column equals some value. We call that a point lookup. We're looking for one value. That's frequently where hash indexes are going to give you the best performance. The second flavor of index is informally called range indexes, which is why I put it in the quotes there. Range is not part of the syntax. You just say plain old non-clustered, and to me that just looks so weird. We have non-clustered hash, and then we have non-clustered nothing. I like things to be a little bit symmetrical. So I talk about them as hash versus range indexes, but in your syntax when creating the table, if you don't say hash, it means range. And Microsoft, the engineers at Microsoft that I was talking to when I was writing the book, sort of wanted me not to use the word range because it's not part of the definition of the objects, but I needed something to call them. So I didn't follow their advice. And then in 2016, when I was exploring some of the metadata, some of the internal metadata for the in-memory tables actually uses the word range. Aha! They were caught in the act. Okay, I'm using this word range. You guys use it internally, so I'm going to use it too. Range indexes do have some ordering to the data. We're not going to be able to look at the details, but they can be good for range searches, for data that you need sorted, or if you have no idea how many buckets to create. It's actually a better idea to have a range index than to have the wrong number of buckets. If you know how many unique values you're expecting, a hash index can be just fine, but to misjudge the number of buckets is worse than anything. And indexes are never written to disk in the streaming behind the scenes. All that gets streamed out is the data rows. They're only an in-memory structure. So here's a picture of our hash indexes, and the assumption is that you know a little bit about hashing. If you don't, you'll either have to go learn about it on Wikipedia, or I do talk a little bit more about it in my books. And I will mention, I do have the hard copies here, 2 of them that I'm going to give away, but this is a Redgate book. The Redgate books are all available for free on the Redgate site in a PDF format. So if you just want to download a PDF, just go to Redgate Bookstore. You can easily find it in a search and look for my name, and you'll be able to find that book and get all the background that I'm having to skip over here. But here's a picture of 3 rows, free floating in memory, but we created 2 hash indexes on this table. I've got a hash index on name. I've got a hash index on city. So there's 3 different values for name. Each one of them has been added to a different hash bucket. So Jane hashes to this first bucket. So there's a pointer from the first bucket to this row with Jane in Prague. There's a pointer in the third bucket to John in Prague, and a pointer from the fourth bucket to Susan in Bogota. I have another index on city. There's the third bucket points to Prague, But there's 2 rows for Prague, so they are linked together. Jane in Prague has a pointer to John in Prague. If there were multiple Janes, each Jane row would point to the next Jane row. Or if we updated the Jane row, there would be another version of the Jane row, and the multiple versions are linked together. There's just different timestamps. So someone looking for Jane would find all the Jane rows, and they'd have to look at the timestamps, which are these first 2 values, 50. This row was inserted at time 50, and the infinity marker means it has not yet been deleted. This row was inserted at 100 and has not yet been deleted. This row was inserted at internal timestamp 90 and was deleted at internal timestamp 150. But that's as deep as I'm going to go into the hash indexes just as the background. Range indexes are built as trees. A range index is a tree that can grow and shrink as you add different values. It's a little bit different than your normal trees for your disk-based clustered and non-clustered indexes. There are pages that point only to the next pages. There are no previous pointers. What we store is keys and pointers to a chain of rows with matching values.
You mentioned that the storage, when it slowly puts it into storage, that the indexes are not stored.
All that gets written out to disk as you make changes is the rows themselves.
My question is, I guess it's rebuilding the index in memory if you're rebooting the system.
When you reboot, SQL Server has to reconstruct the connections as if you're just doing inserts, a restore or a recovery for your in-memory tables, basically. There are some optimizations, so it's not quite as slow as 1 row at a time, but that is probably one of the least efficient parts. I'm not going to say it's inefficient, but because I haven't really noticed major slowdowns, but when you start to measure things, it is slower than restoring a database that doesn't have in-memory tables. It does have to rebuild them a row at a time and build all the linkages, all the pointers for the hash indexes, and there's also pointers in the range indexes. Question here.
Does that mean that when this rebooting, does that actually wait for all the indexes to be created in memory before the query that table, or is it just
recovery always takes time. Even if you don't have any in-memory indexes, recovery takes time to make sure that all of your transactions have been appropriately rolled forward or rolled back. There's always time for recovery. Sometimes it's so fast you don't notice it, but it always takes time to recover. For a database with in-memory tables, it may take a little longer, and it will not be fully recovered until all your in-memory tables are rebuilt and all the pointers to all the rows are reestablished. Question here.
Kalen, so for instance, if I have 1 million row in-memory table and I deleted 999,000 and I didn't back up the log, will it actually have to go through the log and recover now 1 million rows?
Good question. Oh my gosh. What if most of your rows have been deleted? Well, what gets written out to disk is not just the rows that have been inserted, but also the row IDs of the rows that have been deleted. During recovery, before it starts loading these rows in, it will actually build a filter based on all the deleted rows, and if a row has been deleted, its row will not be reloaded.
Yeah, but it has to scan the checkpoint files?
It writes them out into these external files. Yes, the files will have to be scanned, but there's a number of optimizations where it may not even have to look at all the files. There are cases where recovery can take a long time. If you just deleted 1 million rows and you maybe shut down before a checkpoint happened or something like that.
I'm asking that because I know that it's in production and it's a queue table. Basically, the queue is like a very short 100 rows, but it constantly deletes.
half an hour to restore when it's just, to recover, I mean, yeah. There may be some optimizations. I would have to look more at the details. But yeah, there are, as I mentioned, this is one place where it falls a little short of the disk-based tables. And most times it isn't noticeable, but there may be exceptions. So, and this leads into the next slide. Thank you so much, Danny. Just perfect segue there. The database is recoverable in case of failure from a set of files. These are the files that actually get created out there in the file group. We call them checkpoint files because it's a checkpoint that will actually write all your change data out there. They contain each file contains all the rows that were inserted between two timestamps. So everything between 0 and 100 is in this file. Everything between 101 and 200 is in this file. It's usually not quite so neat, but each file contains rows inserted in a particular time frame, and then each set of inserted rows has a corresponding file we call a delta file, which is the row IDs of which of those inserted rows really don't exist anymore because they've been deleted. Those are the delta files. SQL 2016 added 2 additional flavors of files to keep track of large object data, and something called a root file, which helps SQL Server keep track of all the other files a little more efficiently. Question here.
Just a question about the new 2019 accelerated recovery feature. Would that apply to memory, or is that just...
You know, that's a good accelerated recovery in 2019. You know, I started looking at that, and then I got sidetracked. So I'm not exactly sure what's going on behind the scenes for the accelerated recovery. I'm going to say it's a completely separate thing and would not impact this. Don't quote me on that. And I'm sure it's in the recording, so someone's going to quote me on it. But I'm pretty sure it's a completely separate thing and would not affect this behavior. But wouldn't it be nice if it did? All right, so let's take a look at an example just to create a database with in-memory tables. So okay, so I've got several in-memory databases I'm going to create in the next demo, and so if I still have those, I want to get rid of them. And then I create just a default database here. After whatever was there is dropped, all I do is say create database in-memory database. I'm calling it IMDb, in-memory database. It's a regular database at this point. But the first thing I do to make it special is add a new file group which contains memory-optimized data. And then I add what looks in the syntax like a file, add file, but it's really adding what we call a container, which is a folder. So if I go out to disk and I look at, let's open up a different one. I go out to disk. I meant to have this open. And I look at my C drive. I have a folder I've created out here. Wait a minute. Zoom It isn't working with this projection system. Darn. Well, this magnifies. Right, so you can see I have a folder there called HK Data for Hackathon Data. Right now, I've just created this, and you don't have permission? This is my computer. Right now, in this folder called HK Data, there is now a subfolder called IMDb Memory Optimized Data, MOD. That's the name I gave it, IMDb MOD. And then it created this folder called HK version 2, but it's empty. Nothing's there yet. As soon as I create the first table, though, it will become populated, even if I don't put any data in the table. So I'm going to use that database. I'm going to show you that the database files, there are 3 of them. There's the file for regular data, there's the log file, and then the file for the in-memory data is a file stream file. Internally, it's stored exactly like file stream. For the file groups, it says that we have a memory optimized data file group. I'll skip some of these, which are just more informational. I want to show you creating a table. So basically, it looks like a regular create table, but then the indexes, if they are non-clustered hash, do specify a bucket count. So I have 2 hash indexes. Actually, I have 3 hash indexes. They're all hash indexes in this case. And then the final thing that's different is to specify that it is a memory optimized table. That's the crucial feature here. This is how SQL Server knows. It is a memory optimized table, and then we can specify either schema and data or schema only. Schema and data is the default. So as soon as I create this table, I can go back and look at that folder, and it's now been populated. I've got a bunch of folders, files out here in this HKV2 folder. These are all of the checkpoint files, and you can tell by the size what's going to go in them. The biggest ones are for the data rows. The next biggest ones are for the delta, and then the smaller ones, 2 meg and 1 meg, are for any lob data and the roots. But we're not going to go into more details there. Just the size initially lets you determine what kind of file it is. So I'm going to populate, so that the files get created as soon as we create the table, whether or not there's any data. I'm going to put 1,000,000 rows in here just to show you what that looks like, just randomly generating some values here. Well, I'll pseudo randomly. And in just 4 seconds, I created and inserted 1,000,000 rows into this table. I might notice that out on my file system, I still have the same number of files here. All right, nothing special there. Sometimes I notice some special things. I can look at how many rows, and really fast it counts to 1,000,000 and comes back and tells me there's 1,000,000 rows out there. So that's the basics in a nutshell. In-memory database, people say in-memory database, but it's really the database is capable of holding in-memory tables. It's the tables that are in memory. Not all your tables have to be in memory. I can create some tables in memory and some disk-based tables. SQL Server allows me to join those tables together. I can have stored procedures that access both in-memory and disk-based tables. And what a lot of people do with this technology is just start really small. Just take 1 or 2 crucial tables, the tables that have the most locking, the tables that have the most I/O as you're trying to read them in. Put those in memory, and everything else can stay on disk, and just till you get comfortable and notice what an improvement just 1 table can have, and then maybe a few more. Of course, there's a price to pay. You need the memory to support the table and all of the changes to all the rows, but for a lot of people, the performance benefit of doing this will make it easily worth their while. A couple more questions here, yeah? The general recommendation is at least as many, up to 2 times as many buckets as the number of distinct values you're expecting. Bucket count, what you want to try and aim for is to have each unique value in its own bucket. And if you have 1 to 2 times the number of buckets as values, you have a good chance of that, but it is never guaranteed with hashing. It's possible that you can still, the way hashing works is just takes the input value, crunches it through a formula, and comes out with which bucket to put it in on the other end of the function. The more buckets you have, the more spread out your data will be, but there's always a chance that two different input values will crunch together and end up in the same bucket. The more you have, the less chance of that. But the more buckets you have, the more memory it takes. Each bucket takes a little bit of memory. So you don't want to just say 40 zillion buckets, just to be on the safe side, because that's going to eat up memory you'd rather use for your data rows. Question way back here. I'm sorry? Reallocate the memory. There is some configuration, but there's no way to actually say reserve this memory for in-memory tables. There's a little bit of tweaking you can configure for what memory is used for what purposes. You can use resource governor a little bit and set a maximum memory maybe for other file groups. There's something you can do with resource governor. I'd have to take another look at it, but it's just sort of trying to do the best you can. There isn't any way to just say, I want to make sure there's this much memory for my in-memory tables. Question here.
Is there any recommendation for the placement of the file group file for memory? Like its own dedicated drive, or put it on the same as a log? I mean, or even whether it's even worth creating more than one file, it's all.
In 2000, so should these containers be placed in any special places? I haven't seen any research done testing on that yet. If you're using a smart drive system, usually that's the least of your worries. And you just let the drive system figure it out. As far as multiple, there were some reasons in the original version why having multiple containers gave you some advantage, but that was in 2014, and then they optimized it in 2016 and wasn't an issue anymore. Question here.
Can memory table be replicated using transaction replication?
I used to know that. I'm going to say I don't. Well, you write to the log. It writes to the log. You can't replicate. It can be a subscriber.
What about AG? Always on? No?
I think you can replicate it, but you cannot replicate two in memory.
He's saying it's the opposite. It does get logged. So, yeah, I'd have to look at that again. Yeah, some of the restrictions, at least in the first few versions, there wasn't a specific technical reason. It was just because they hadn't tested it thoroughly enough, and they decided better safe than sorry. So there were a lot of restrictions in the first release that they realized for the second release that really weren't necessary. And it may be that some of these restrictions will be eased going forward, but I can't remember. I would have to recheck it, and it might even be in the book, but I don't remember. Question in the front.
How do you calculate how much memory you want to put in your hardware for a table?
How do you figure out how much memory you need? Well, there are formulas that you can look up to see how much memory each row will take based on the data types, just your data itself. The number of overhead bytes is a known value, and I can't remember what it was, but I've got it in the book. Well, no, you have to know how big your rows are, but it's per table. So you would start by looking at a space used for the table, but you have to have enough memory for all the changes to all the rows. They're eventually cleaned up when nobody needs them anymore, when there are no open transactions that could possibly want this table, but sometimes it's a little slow to get rid of everything. It has a garbage collection process. But yeah, you'd have to figure out the base size of the table plus the overhead for all these extra bytes at the beginning, plus what volume of changes you're expecting, and make sure you have enough for all of the updated rows. I want to move on because there's still a bunch I have to cover. We'll have another question opportunity a little bit later. I've just got a couple of quick slides showing you some of the changes in the first subsequent versions, 2016 and 2017. Most of the really frustrating limitations were removed in 2016. In 2016, you can create constraints, unique constraints, foreign key, and check constraints. Primary key constraints were already allowed, but if you couldn't have a foreign key, its value was minimal. Check constraints and triggers, although the triggers do have to be natively compiled. Alter table is available now for in-memory tables, so you can make changes. You can change the bucket count, for example, if you realize you've made it too small. People were real excited when they first saw this, but then upon testing, it actually turns out that behind the scenes, SQL Server is actually dropping the table and recreating it. It's easy for you to just type in an alter table, make it 2 million buckets instead of 1 million, but SQL Server is actually completely rebuilding the table. Memory optimized tables can be created in an Azure SQL database without any pre-configuration necessary. In Azure SQL DB, you don't define your files or your file groups. You create an Azure SQL DB, you can just say create table with in-memory as an in-memory table. The create table that I showed you would just run in an Azure SQL DB. You don't need the binary collation for indexed character columns anymore. Column store indexes can be, oops, typo, can be created for in-memory tables. I've got a whole section in the 2016 book about column store indexes. In 2014, I didn't mention this before, statistics were not updated automatically. They are in 2016. And there were limitations on the kinds of queries you could run against an in-memory table. Not a lot, but some, and some of those were removed, especially what constructs you could put in a natively compiled procedure. Native compiled procedures in 2014 were basically just your really simple OLTP operations, just simple inserts, updates, deletes. You couldn't have subqueries, you couldn't do CTEs, you couldn't do the fancy kinds of joins, only equijoins with no outer joins, a lot of limitations, and a lot of them were removed in 2016. But there's whole pages in the documentation that list the constructs available in your native procedures. 2017 did not add a whole lot of really new, exciting features. They just made things a little bit better. Just still making improvements in performance. They did allow us to examine more easily. The SP space use, which I suggested you use, couldn't be used on an in-memory table before 2017. So you'd have to use other tools to figure out how much space an in-memory table is taking up. There were dynamic management objects that would help with that. SP rename could be used, space use can be used, and more than 8 indexes are possible. Not that I recommend it, but if you really, really want more than 8 indexes, you've got that option now. The file groups can be stored in Azure Storage if you're using a VM, for example, where you're actually defining your files and where they might go. You can actually put them in the Azure Storage. And computed columns were made available. That's probably the biggest feature added to 2017 is that computed columns can be used in in-memory tables. So 2019, a couple of big changes that we're going to talk about in a little bit of detail here. TempDB has been a source of contention for many, many versions now, where if many tables are being created at the same time, there's contention, blocking that shows up in the system tables and in some of the other system structures when you're using TempDB for what it was intended to, creating lots of small temporary objects. So 2019 made a change in TempDB that it uses this hackathon technology by default. You don't have to do any special setup. You don't have to flip a switch. You don't have to create special files for TempDB. It's an automatic thing in 2019 for TempDB. A set of the system tables, and in just a couple of slides, I will show you what those tables are created as in-memory tables by default. So why is this important? What is the actual problem? Well, there are two actual problems that are being solved by creating these system tables in memory. The first is an allocation issue. Those of you that have read in detail my earlier books where I detailed how SQL Server allocates, extends, and keeps track of what's been allocated might remember some of these. But for those of you that are not well versed in it, this might be new information. Every file in every database, not just TempDB, every file in every database has some special use for the first few pages. The first page is actually a header that we won't talk about, but page 1 is always a special page called a PFS page, page free space. It has 1 byte for each page in the file that helps SQL Server know, is this page completely full or is it half full? Is there room for more rows? There is a new PFS page every 8,087 pages. So page 1, page 8,088, add 8,087 to that, and there'll be another PFS page. But it helps SQL Server know where there are pages with room for new rows. Page 2, the third page of every file, is what we call a global allocation map. This helps SQL Server know what extents are available for new tables or for a table to grow. And there's a second GAM page every 63,904 extents. I usually just round it off and say 64,000, but I didn't create the slide, and the person who did wanted to be exact. Usually, those of you who have read my stuff know I usually like to be exact too. But when the math is so easy with 64,000, I usually go with that. So SQL Server doesn't care if the math is easy or not. It can add 63,904 as easily as it can add 64,000, so we'll go with that. So there's a global allocation map page every 63,904 pages, and another allocation page called a secondary. Some people call it a secondary global allocation map. Some people call it a single page global allocation map. Some people call it a shared global allocation map. Take your pick. I'll start with this. SGAM is the other name for it. GAMs and SGAMs always go in pairs. They help SQL Server keep track of special kinds of allocation we won't be talking about, but those also exist every 63,904 pages. They keep track of what extents have been allocated to a file or what have been used. So the PFS looks in an error message or in a page deciphering as file number colon page number. So file 2 is usually, database colon file colon page. Database 2 is TempDB. File 1 is usually your MDF. And then page 1 is a PFS. So if you get messages about contention on that page, you know it's a PFS contention. So every file has basically the same structure, except the log file, which is completely different. But every data file, MDF and NDF, always has a PFS at page 1 and every 8,087 pages thereafter. Every file has page 2 as a GAM, and every 63,904, every file has page 3. So when you see one of these pages has contention on it, you'll know it's an allocation problem, which usually occurs because there's too much allocation going on. you have a stored procedure that's creating temp tables, and lots of people are running this stored procedure at the same time. Well, that's something you can do with stored procedures. And temp tables are a wonderful thing if they're not going to stick around. But if hundreds or thousands of people are doing it at the same time, you can end up with contention on these pages, and putting these pages in memory helps solve the problem. The metadata itself also can be stored in memory. When you create a table, there's a whole list of tables that need to be modified. When you create a table, there's, well, the sysObjects, which is now a view. It's based on some real tables, but we'll use the old names, the known names. SysObjects gets changed when you create a new table. SysColumns, there's a table called SysTables. There are SysConstraints and there's foreign keys. All kinds of tables have to be adjusted every time you create a new table. And under the covers, there's a table called SysObject values, which we normally don't look at. But a new table's created, and what this is showing you is that SQL Server behind the scenes is inserting into all these different system tables, which causes contention problems. So, starting in SQL Server 2019, all of these tables here on the left-hand side, in the left-hand chart, all of these tables are now automatically stored in memory. The two over on the right, sysRowsets and sysalloc units, will become in-memory tables in a later release as part of 2019. Maybe a CU, maybe a service pack, which they're not doing so much anymore, but it's planned for the very near future to add 2 more tables to this list. So I can actually show you a few things that are different once we have the table stored in memory. And how much time do I have left? Originally, the slide told me the time, but then when I didn't do presenter view, I lost that. Oh, I've only got about 13 minutes left. All right. This is a real quick demo here, just to show you a couple of things that are different when the system tables are stored in memory. First of all, there is a dynamic management object to show you information about your in-memory tables. Any DMV that has the letters XTP means it has something to do with in-memory tables. XTP stands for Extreme Transaction Processing, really fast. So XTP is your clue. This has to do with in-memory. And in the tempDB database, if I look for tables stored in DMDB XTP object stats, there are 10 of them. The 10 tables that I just showed you are stored in memory, and there's information available about them in this view. We're not going to look at the details of what's available there, but just to show you there were 10 rows there, where if I run exactly the same query in a user database, no tables at all. The tempDB database has in-memory tables by default. And then the other part of this demo is to show you some blocking that exists in a user database. And you can use, if you want to duplicate this, I will make the scripts available. You can use any database because it's going to create a brand new tiny little table. I'm just using my test database. I'm going to create a little table called test1, tiny little table. Oops, and close all my other windows. Now another transaction's going to start and create another table. Those two are fine, but when I go back to the first one, in my user database and try to do an insert now, this is blocked. two connections, both have created a temp table, and now it blocks either one of them, you would see, is blocked from doing any inserts into that table. And nothing's going to happen until one of them actually gets rolled back. I'm going to actually stop that, roll back the transaction, roll back this transaction, and then do exactly the same thing in tempdb. Switch to tempdb here. In tempdb, I will create this little teeny table. In tempdb, another session will create another table. And then when we go back here and try to do the insert, there is no blocking. Feel free to ooh and ah. So just to show you, yes, there is something different now. Less blocking in tempdb because of this new added technology. So the last thing we're going to look at is snapshot databases. Snapshots were actually added way back in SQL 2005. What a snapshot is logically, it's a copy of your database at a point in time. It's not stored as a complete copy. It's stored just as the changes. Every time you make a change, the original version of the page is copied elsewhere. So we know what the original database looked like. The unchanged pages stay available and are shared among all the snapshots, and the changed pages are written elsewhere so that the source database can still see the changes. I'll show you what that looks like. We've got a little animation on the next slide. If you have multiple snapshots, it can end up affecting the performance. It doesn't come for free, but it's a really fast way of being able to see versions of the whole database. And in the original technology, we can actually do a restore from a snapshot. We create a snapshot of our database right before we're about to do something really risky, maybe run some process that's supposed to change a bunch of the data and it doesn't work. We've changed everything to the wrong value, or maybe, I know this has not happened to anybody here, but I've heard rumors of people that forgot a where clause and changed every single row in a table. Nobody here ever did anything like that, I'm sure. Of course, I never did anything like that. But if somebody you knew did something like that, the whole table's munged up now. If you had a snapshot, you could just say restore to that snapshot much, much faster than restoring the database from a backup. It doesn't help if there's a disk crash. You've got real backups for that. But if there's a logical data error, data has been changed inappropriately, restoring from a snapshot can be a much faster way of fixing that. So here's an illustration of the original snapshot technology. So I have this database called MyDB. I'm just showing you the first 16 pages here. And I create a snapshot of this database. Initially, SQL Server just creates a shell. There's really nothing there. It creates a shell of the same size, but right now, we haven't made any changes, so anybody trying to select from MyDB snapshot is going to see the same data as if they select from something in MyDB. No, there's nothing different. But then somebody comes along and does an update. They use the original database, and they end up doing an update that behind the scenes updates pages 4, 9, and 10. So before we change page 4, we write it out to the snapshot file. Page 9 gets written out. Page 10 gets written out. So the source database has new data on pages 4, 9, and 10. But we have the old version of the pages stored out here in this new structure. So if somebody uses the snapshot and does a select that ends up needing data from pages 4, 6, 9, 10, and 14, They will read page 4 from the snapshot. 6 hasn't changed, so that can be read from the original database. 9 and 10 are read from the snapshot, and 14 is read from the original. Anybody using the original database sees the changes in red, but anybody using the snapshot, SQL Server has to determine whether the page they want is a changed page or not. The changed pages are read from the snapshot. The unchanged pages are read from the source. This is a really cool technology. If you've never experienced it, you might want to go play with it a bit. And then if somebody totally messes up the original database, the changes are available through the snapshot. You can do it's called a revert to the snapshot, so whatever in the snapshot becomes the real data. 2019 allows you to create a snapshot on a database with in-memory data. Hekaton storage was completely redesigned so that the data files on disk could be shared. 2 different databases could write to them as changes were happening. Duplicate delta files had to be created so that the snapshot would use one and the source would use another. And SQL Server is much more cautious about removing these external files in case because it has to make sure that there aren't any snapshots out there. The biggest limitation is that you can't do this revert. It only allows you to see multiple versions of the whole database at the same time. So just a real quick demo here to finish up. I'm going to use basically the same script I had before. Drop my IMDb database. Create a new one. And this is what it looks like to create a snapshot. You just make a copy of every file except the log file. There's no log file for a snapshot. That works perfectly well. Well, that was just to show you there was no error. I want to drop it right now because I want to make it a database capable of holding in-memory tables. So I'm going to create a file group. And I'll tell you, when I first was playing with this, I discovered a bug. Brand new feature, my first time with it, and I discovered a bug. How about that? I created the file group, but then when I tried to create the file, I had a typo and didn't realize it, so the file was not created. I tried to create the snapshot, and I got this error message that said the snapshot feature is not supported with databases that have memory-optimized file groups. And I said, this doesn't work yet. And the engineer I was working with said, yes, it should be, and it didn't work. I got this error saying it's not supported. Well, the bug is really that it's the wrong error message, because my problem was just that I hadn't built the file or the container. Once I do that, then I can create a snapshot. And it doesn't say it's not allowed because it is allowed. So now I have a snapshot of the initial database. I'm going to use the database and create a table. And then create another snapshot called IMDb2 snapshot. Oops, and I didn't grab enough. And I have a second snapshot. I can actually see that there's a folder over here for database snapshots. It's always been there, whether you've used it or not. And it now shows me I've got 2, well, I had one that I was using for earlier testing, but I have IMDb snapshot and IMDb2 snapshot. They're both out there. So what's in, now I'm going to put my million rows into the table. Should only take 4 seconds again. And look at how many rows, 4 seconds. So the base database has 1 million rows in the table. How many rows is the original snapshot going to have? Wrong. The original snapshot. Who said that? Okay, you win a book. Okay, the original snapshot gives me an error message because I created that before the table was created. The second snapshot has the 0. That was created after the table was created, but before I inserted the rows. So I can have multiple snapshots. There actually is not a technical limit, whether in memory or not in memory, but for every additional snapshot, every time you make a change, you've got to push data out to more places, and that's why it starts to affect performance. A colleague of mine was doing some testing, and he didn't really notice any real impact until he had like 9 or 10 snapshots. So you can have a good handful or two, but you don't want 50. Every hour make a new snapshot. I don't recommend that. So it's a cool technology now available with in-memory databases. So I wanted to make sure you had a good foundation for what Hackathon and in-memory storage was all about. Microsoft's expanding on this technology. They're going to be using it for more and more features automatically without you having to do any configuration. But now that you've got a basic understanding, you'll be able to see why these extensions and expansions are really powerful. I gave you some bullet lists of the changes in 2016 and 17, and then drilled a little deeper into some changes in 2019. So thanks very much for being here. You still got another almost day and a half. Thank you so much.